All right, so we begin with the fourth lecture in this series, power series. It continues, but the topics are now listed below. Some of these topics were listed in the previous lecture also. So first thing we'll begin with some exercises on radius of convergence. Then we'll take on exponential and trigonometric functions, and we'll look at their fundamental properties. Then we'll look at the Cauchy product of two power series and differentiation theorems on power series. Then there will be some identities on trigonometric and exponential functions which will need these two results. Then there are some theorems on entire functions. I will tell you what entire functions are. And finally, we will conclude with a theorem called Abel's limit theorem, which is quite useful for understanding boundary behavior of power series, and some more exercises. So, and that will complete this chapter on power series. Then we can move on to other things. Okay. So we'll begin with a longish list of exercises. So determine the radius of convergence of these power series. 1 plus 1 over n to the power n squared, z to the power n, 1 plus 1 over n to the power n squared, z to the power n squared. Third one is sigma z to the power 2n upon n factorial squared. And the fourth one is 3n factorial divided by n factorial cube into z to the power n. And the fifth one is z to the power n divided by n to the power n. Okay. For these 5 power series, use either the ratio test or the root test, whichever is appropriate, and calculate the radius of convergence for each one of these. There are several such exercises. You will find many in Kreyszig's book. Kreyszig does power series in chapter 14. You have got the book by now. So he does it in chapter 14, and you will see lots of exercises on power series. And I just picked up a small sample. Some of these are probably there in Kreyszig, some of these may not be there, and some of these are quite standard. Most of these are quite standard problems, and they will be there in most of the books. You will find lots of examples. The second question is, you are given a power series with center at the origin and positive radius of convergence. The radius of convergence could be infinity, that is allowed. And the sum function is f of z. It is known that f of z bar equal to fz the whole bar for all z within the disk of convergence. What conclusions can you draw about the power series? What conclusions can you draw about the power series? F of z bar equal to fz the whole bar is given to you. This holds for all z within the disk of convergence. So the question is, what can you say about the power series? Can you say anything specific about the nature of the coefficients, for instance? Specifically about the nature of the coefficients. Yeah, anybody can tell me the answer? Suppose f were to be a constant function, or what if f is a linear, suppose if f is a linear polynomial, a plus bz, then what does this condition mean? F of z bar equal to fz bar. Take the simple case, suppose the power series were f of z equal to a plus bz. A polynomial is a power series, right? A polynomial is a power series. Suppose if a plus bz were to satisfy this condition, then what is the conclusion? A must be? Yeah, A must be real and B must be real. So the same thing can you say for general power series, A naught plus A1z plus A2z squared, etc. If this, yeah, so what is your guess? That the coefficients are real. Okay, that's the problem. The exponential and the trigonometric functions. The power series sigma n from 0 to infinity z to the power n upon n factorial has infinite radius of convergence, as we have seen. The sum of the power series is denoted by e to the power z. So the definition of the exponential function in the complex domain is e to the power z is 1 plus z plus z squared upon 2 factorial plus z cube upon 3 factorial and so on, correct. That is a definition of the exponential function. It is one of the most important functions and we must understand its properties. And very closely related to the exponential functions are the trigonometric functions. So, how do you define sin z and cos z? Sin z by definition is z minus z cube upon 3 factorial plus z to the power 5 upon 5 factorial and so on. Cos z is by definition 1 minus z squared upon 2 factorial plus z to the power 4 upon 4 factorial, etc. And what is the radius of convergence of these two series? Infinite. We have seen something similar in the previous lecture, right? Okay. So, the functions sin z and cos z are defined as sin z equal to summation n from 1 to infinity minus 1 to the power n minus 1, right, z to the power 2n minus 1 upon 2n minus 1 factorial, and cos z is n from 0 to infinity minus 1 to the power n z to the power 2n upon 2n factorial. If you put in, it is very clear by looking at these three series. Look at e to the power z, e to the power z is here. So, instead of z if you put iz, instead of z if you put iz, it is very clear that you are going to get e to the power iz is cos z plus I times sin z, e to the power minus z is cos z minus I times sin z. So, the exponential function and the trigonometric functions are closely related, correct, and this is a relationship, the Euler's relations, as you, if you will. Now, we want to understand these functions a little more before you understand the properties of sine, the exponential and the sine, cosine and exponential functions. We need two more theorems on power series. We are not going to be able to prove these theorems in this course. Time, we simply do not have time. Before studying these functions, we state without proof the following two results. The first is a result on multiplication of two series. Suppose sigma n from 0 to infinity a n and sigma n from 0 to infinity b n are two absolutely convergent series, then their Cauchy product is given by, the Cauchy product is this, is this series a naught b naught plus a naught b1 plus a1 b naught, a naught b2 plus a1 b1 plus a2 b naught. If you add the subscripts, it adds up to 2 for the third term, it adds up to 1 for the first term, it adds up to 0 for the 0th term. For the nth term, I start the terms, counting the terms as 0th term, first term, second term, okay. So, in the nth term, it is aj b n minus j, the nth term of the Cauchy product. Remember that we are going to be working with power series, so that you are going to have a 0th term also. Is that correct? This is the Cauchy product of the two series sigma an and sigma bn. The question is, will the Cauchy product converge, number 1, and if it does converge, will it converge to the product of the two things? These are the two questions that will come up. And the theorem says that if sigma an and sigma bn both converge absolutely, then their Cauchy product also converges absolutely, and it converges to the product. It converges to what you expect it to converge to, right. The Cauchy product of two absolutely convergent series converges to the product. Now, this theorem was due to Cauchy. The multiplication theorem that I stated is due to Cauchy. One can ask, can I drop the hypothesis of absolute convergence? Suppose if sigma an and sigma bn are conditionally convergent, then will the Cauchy product converge? Unfortunately, the answer is no. I will probably give you an example later on, perhaps if time permits. It is not true that the Cauchy product of two conditionally convergent series converges. It may not converge at all. Okay. So, I cannot completely drop the hypothesis of absolute convergence. However, It was proved by Mertens. It was proved by Mertens. This above theorem is due to Cauchy. Mertens proved that if one of the two series converges absolutely, it is sufficient. If one of the two series sigma n and sigma bn converges absolutely, the theorem still goes through, right. Mertens theorem is slightly more difficult to prove than Cauchy's theorem. It is easy to prove this theorem, it is not difficult at all. Okay. Now, the third question that we should ask is, suppose I give you two conditionally convergent series sigma an and sigma bn. It may happen that sometimes the Cauchy product may converge. It may happen that sometimes the Cauchy product may converge. Well, suppose I give you the information that sigma an converges, sigma bn converges, and the Cauchy product also converges. The question is that, does the Cauchy product converge to the respective product of the individual series? Is the Cauchy product, if it converges, is the sum equal to sigma an into sigma bn? That is a correct statement. That is true. If the problem is, if both the series converge conditionally, the Cauchy product may not converge at all. But if it does converge, then it converges to the correct value, namely the product sigma an into sigma bn. This theorem is due to Abel. Okay. Now, the other theorem on power series is the differentiation theorem. Suppose sigma an z to the power n from 0 to infinity is a power series with non-zero radius of convergence, and the sum function is fz, then fz is complex differentiable, and f prime z is given by sigma n from 1 to infinity n a n z to the power n minus 1, as long as z is in the disk of convergence. So long as you stay within the disk of convergence, term by term differentiation is permissible. This is a very important theorem because you have been using this time and again in the PDE class. When you computed the series solution of the Legendre's differential equation, you got a power series solution. That power series had positive radius of convergence. So, all the steps that lead to the derivation are now justified because term by term differentiation is valid. And the new power series that you get also has the same radius of convergence. So, I can differentiate it again, correct. So, this differentiation theorem now justifies all the things that you did in your PDE MA 207 course, when you computed the series solutions of Legendre equation, the Chebyshev's equation, the Hermite equation, the Airy's equation, and all those equations. You get power series solutions, and they are all these power series have positive radius of convergence, and so the term by term differentiation, which was suspect, has now been established, correct. So, the differentiation theorem is very important, and so now let us apply the differentiation theorem to the exponential series. So, e to the power z is what? E to the power z is sigma n from 0 to infinity z to the power n upon n factorial. So, I differentiate that thing term by term. d dz of e to the power z is summation n from 1 to infinity n times z to the power n minus 1 upon n factorial, n a n z to the power n minus 1, and again I get this n and this n factorial cancels, become n minus 1 factorial, but it is going from 1 to infinity. So, readjust the indices, and again you get n from 0 to infinity z to the power n upon n factorial. In other words, d dz of e to the power z is again e to the power z. By the way, I have not said this, but so this appears now formally in the slide, that another notation for f prime z is d dz. d dz stands for complex derivative. Okay. Now, similarly, the sine function and the cosine function are defined in terms of a power series converging for all values of z, right. So, term by term differentiation of the sine series will give you the cosine series. term by term differentiation of the cosine series will give you minus the sine series. So, you have the formulas d dz of sine z is cos z and d dz of cos z is minus sine z. Okay. So, now let us calculate d dz of sine squared z plus cos squared z. Use the product rule. It is 2 cos z into minus sine z plus 2 sine z into cos z. So, the derivative of sine squared z plus cos squared z is 0. And so, sine squared z plus cos squared z is a constant. How do I determine the value of the constant? Evaluating it at a specific point, and the most convenient point at which I can evaluate it is 0, z equal to 0. Put z equal to 0 in the series, cos 0 is 1, sine 0 is 0. So, sine squared 0 plus cos squared 0 is 1. So, sine squared z plus cos squared z is always 1, correct. This also was in the real case, just as in the real case sine squared x plus cos squared x is 1, here we have sine squared z plus cos squared z is 1. Is it clear? Now, there is one little difference. In the real case, this equation has an important meaning. If z were real, say if z were equal to x, real number, then cos x and sin x are both real. Therefore, I have sums of 2 squares which is 1, and so cos squared x is less than or equal to 1 and sin squared x is less than or equal to 1 and minus 1 less than or equal to sin x less than or equal to 1, minus 1 less than or equal to cos x less than or equal to 1. Sin x and cos x are bounded when x runs over the real line. There is no such conclusion from here. There is no such conclusion available. If z is a complex number, sin z and cos z are not bounded functions. Now, let us apply the product theorem. We have seen some applications of the differentiation theorem. Let us see an application of the product theorem. Let us multiply e to the power z1 and e to the power z2. E to the power z1 is sigma n from 0 to infinity, z1 to the power n upon n factorial, sigma m from 0 to infinity, z2 to the power m upon m factorial. Take their Cauchy product. The nth term of the Cauchy product is sigma n from 0 to infinity. Nth term is sigma j from 0 to n, the jth term from here and the n minus jth term from here. Z1 to the power j upon j factorial, z2 to the power n minus j upon n minus j factorial, multiply and divide by n factorial, and you get 1 over n factorial times n choose j, z1 to the power j, z2 to the power n minus j, sum goes from 0 to n. So, now what is this object here? Over here, whatever you have here is z1 plus z2 to the power n. So, you get e to the power z1 into e to the power z2 equal to n from 0 to infinity 1 over n factorial z1 plus z2 to the power n, right. So, you have sum from 0 to infinity 1 over n factorial into z1 plus z2 to the power n, correct. What is that? Some problem with their, okay. Once again, e to the power z1 into e to the power z2 is summation n from 0 to infinity 1 over n factorial. Why is it not producing? There it is. E to the power z1 into e to the power z2 is sigma n from 0 to infinity 1 over n factorial into z1 plus z2 to the power n, which is e to the power z1 plus z2. Right. So, now e to the power iz is cos z plus I times sin z, e to the power minus iz is cos z minus I times sin z, cos z is 1/2 of e to the power iz plus e to the power minus iz, sin z is 1 over 2i of e to the power iz minus e to the power minus iz. So, we have these two identities and we have this exponential addition theorem. Some exercises for you. Prove that cos z1 plus z2 is cos z1 cos z2 minus sin z1 sin z2. Prove that sin of z1 plus z2 is sin z1 cos z2 plus cos z1 sin z2. Prove that cos iz is cos z. So, in particular, if you allow the y to be real number, cos iy is cos y, sin iy is I sin y, right. So, cos y, the graph of the cos y goes off to infinity, right. Cos y is what? 1/2 of e to the power y plus e to the power minus y. So, cos y goes to infinity when y goes to infinity. So, cos of iy goes to infinity is a real number and going to infinity as y tends to infinity. So, cosine function is not a bounded function. Likewise, sine function is also not a bounded function. Thus, mod cos z and mod sin z are unbounded on the complex plane. Very different story from what you see in the real domain, right. Shall I move on to the next slide? No? Hurry up, hurry up. So, you have the addition formula for trigonometric function. You can of course do it in several ways. You could try to use the differentiation theorem rather than do the multiplication of this and adding it up. Use the exponential addition theorem. Use the exponential addition theorem and get this result. Write this in terms of exponential functions and use exponential addition theorem and get this result rather than using the multiplication theorem again. Okay. Now, prove that e to the power minus z is 1 over e to the power z. So, e to the power z never vanishes. So, e to the power z omits the value 0. E to the power x plus iy is e to the power x into cos y plus I times sin y. So, I am going to here allow x and y to be real. I am going to allow x and y to be, of course, it is also true when it is complex, but because the exponential addition, because the product theorem, but it's interest, this particular identity is particularly interesting when x and y are real. So, e to the power x plus iy is e to the power x into cos y plus I times sin y. Use this to show that the exponential function e to the power z attains all complex values except the value 0. 0 it cannot attain, it attains all other values, correct. The next question is, do the functions sin z and cos z attain all complex values? That is what you have to investigate. Write sin z as 1 over 2i e to the power iz minus e to the power minus iz. Set it equal to a, then you have to understand whether this expression is equal to a. You get a quadratic equation for e to the power iz. Investigate and do it. Okay, done. Shall we proceed? The next thing is entire functions. What is an entire function? Suppose fz is a sum of a power series with infinite radius of convergence, then fz is said to be an entire function. So, what is entire functions? Entire functions are those functions which have a power series expansion where the power series is valid over the entire complex plane. A polynomial is an entire function, e to the power z is an entire function, sin z is an entire function and cos z is an entire function. Are there other types of things? Of course, e to the power sin z is an entire function, sin of z squared is an entire function, e to the power z squared is an entire function, but other than these combinations that you can make using polynomials and exponential functions and trigonometric functions, are there anything else? The Bessel's function of order 0, for instance, is a entire function. What is J0 of z? You have studied that in the PDE course. What is J0 of z? It is given in terms of a power series. We also studied this in the previous course, MA 108. There was a chapter on Bessel's function in the last course, right. So, J0z is sigma n from 0 to infinity minus 1 to the power n upon n factorial squared z by 4 to the power 2n. Check that the radius of convergence on the right hand side is infinity. So, the Bessel's functions of positive integer orders, they are further examples of entire functions. Jpx is an entire function when p is a non-negative integer. J half is not an entire function, by the way. P is integer and p is non-negative. And what is J0 prime? Minus J1. J0 prime is also, which is, so J1 is also an entire function, right, for example. So, the theory of entire functions occupies a very distinguished position in the theory of functions of a complex variable. In the early history of the theory of functions, considerable amount of work was done on entire functions by Hadamard and other people. The next example is that of the gamma function. The gamma function is defined to be the integral 0 to infinity e to the power minus t, t to the power z minus 1 dt. It turns out that this gamma function is complex differentiable on the right half plane, and it satisfies the functional equation gamma z plus 1 is z gamma z. Using this functional equation, I can define the gamma function for other values. I can divide by z over here, and I can define gamma z as gamma z plus 1 upon z when real part of z is bigger than minus 1, except at the origin. At the origin, because I am dividing by z, I am going to run into trouble when z equal to 0. When z is not equal to 0, gamma z plus 1 upon z is well defined. Denominator is z, numerator is gamma z plus 1. Now I can allow the real part of z to be bigger than minus 1. So I can, by this process, I can extend it to the complex plane minus 0, minus 1, minus 2, minus 3, etc. The plane with these points removed, the gamma function is a complex differentiable function. Now, one can show that the gamma function satisfies the Euler's reflection formula. Gamma z into gamma 1 minus z is pi by sine pi z, and this is going to be valid whenever z is not a integer. From this equation, what do you get? You gather that gamma z cannot be 0. This equation will tell you that gamma z can never be 0. If gamma z is never 0, that means 1 over gamma z is a perfectly nice function. And it also turns out that at 0, minus 1, minus 2, those forbidden values, gamma function becomes infinite, and so 1 over gamma z is 0. So by this process, one can define 1 over gamma z everywhere, not only at complex plane minus 0, minus 1, minus 2, etc. At these forbidden points, you define 1 over gamma z to be 0, and 1 over gamma z is an entire function. It's a very important entire function. This was studied by Weierstrass in very great detail in 1856. Of course, the details of this last example need further elaboration, but we will come back to it later if time permits. This is just an example at this stage. You can just, the details are not completely filled in, but one can always fill it, right. So, we have lots of examples of entire functions outside of sine and cosine. Sine and cosine are important. Exponential function is a very important function. Polynomials are entire functions. Exponential function is an entire function. Sine and cosine are entire functions. But other than these, there are plenty of other examples of entire functions. The Bessel's functions give you an example of provide a sequence of entire functions, and the reciprocal of gamma function 1 over gamma z is an entire function, and one can have many others. Now, why is the theory of entire function? Now, I say that the theory of entire functions is a very distinguished branch of complex analysis. So, out of this distinguished branch, let me give you a sample of two important theorems on entire functions. The first is a Liouville's theorem. A bounded entire function is constant. A bounded entire function is constant. Entire function cannot be bounded. The next theorem is the little Picard's theorem. It's called the little Picard's theorem so as to distinguish it from another deep theorem called the great Picard theorem. So, although it's a little Picard theorem, it's quite difficult to prove this theorem, and its proof is outside the scope of this course. The statement is certainly interesting, and I can tell you right now. What does the little Picard theorem say? That an entire function that omits more than one value is a constant. An entire function can omit one value. Exponential function omits the value 0. Does a polynomial omit more than one value? If a polynomial is non-constant, it takes on every value. That is the fundamental theorem of algebra. And I asked you a question, does sin z and cos z attain every value? What was it that I asked you to do? Write sin z equal to a, take an arbitrary number a, right? Take an arbitrary number a, right? Take a, and I want to solve the equation sin z equal to a. Write it as 1 over 2i e to the power I z minus e to the power minus I z equal to a. Put the 2i there. So, e to the power I z minus e to the power minus I z is 2ia. What is this? This is a quadratic equation in e to the power I z, correct? I can solve this quadratic equation using the quadratic formula and obtain e to the power I z, correct? The moment you get e to the power I z, use the fact that the exponential function attains all values except 0, and then examine whether there will be a z such that you can get this. That would be the pedestrian way of going about the job. Very interesting thing happened when I was teaching this course to MA 204 students, the BTech students. Since you are all college teachers, this is very relevant for you. This example is very relevant for you because I asked this question in the examination, in a test, class test, and a group of students gave a very elegant solution to the problem, and here is what and their solution I am constructing as an exercise. Use little Picard's theorem to show that sin z attains all complex values. Now, the solution that was given by these students was the following. Sin z surely attains the value 0, sin 0 is 0. Suppose it misses the value a, then it will miss the value minus a also, no? Because it is an odd function. Sin z is an odd function. So, if the value a is missed, then the value minus a will also be missed. So, by little Picard's theorem it will be a constant, which evidently it is not. So, sin z attains all values. This beautiful solution was given by a small group of electrical engineering students of IIT Bombay who took this course in the year 2004. So, I am recording this in this slide, and okay. Now, next exercise, suppose if f and g are entire functions such that e to the power f plus e to the power g is 1, what can you say about f and g? This is an exercise from Raghavan Narasimhan and Nivergel's textbook, Theory of Functions of One Complex Variable. This published by Berkhauser Verlag. This is available in Indian edition. Narosa has reprinted it, and this book is available in Indian edition. Raghavan Narasimhan and Nivergel. Raghavan Narasimhan's book was earlier book did not involve the second author, but then with the second author there is a nice list of exercises in the book. It's a difficult book, I am warning you, but for those who are interested in learning complex analysis, this would be a beautiful place to start learning. There is a proof of the little Picard's theorem in this book, among other things. It's difficult, but very rewarding book. So, now the exponential function omits the value 0. The function sin z and cos z do not omit any complex value. The fundamental theorem of algebra says that a non-constant polynomial does not omit any value. The values that are omitted by a function, by an entire function, are called exceptional values. So 0 is an exceptional value of exponential function. Sine and cosine do not have exceptional value. Okay. So the proof of Liouville's theorem will be done later. Now the little Picard theorem is very deep, too deep for a first course, but deduce the Liouville's theorem from the little Picard's theorem. This is more of an exercise. This should not be, one should not do this. Well, suppose an entire function is bounded. That means that its values are all constrained to be in a disk. So it omits so many values. So by little Picard's theorem, it's a constant. So of course, the purpose of this exercise is to show that the little Picard's theorem is a strengthening of the Liouville's theorem. Liouville's theorem itself is very important, but a considerable considerable improvement on Liouville's theorem is the little Picard's theorem. The next exercise is, suppose you take a polynomial Pz, which is z to the power n plus a1 z to the power n minus 1 etc. plus an. Let us, you take a polynomial, show that there exists R naught such that mod Pz is bigger than or equal to 1/2 of z to the power n for all z outside. What it is saying is that outside a large disk, it is the leading coefficient that really matters. What is the polynomial? Which polynomial I took? I took z to the power n plus a1 z to the power. So you see, when z is large, I can, these things become much smaller than this term, correct? The z to the power n term is the one that dominates, but I can't say that mod Pz is bigger than or equal to mod z to the power n. That will be wrong. It will be bigger than, mod Pz will be bigger than or equal to half of mod z to the power n. When I say that these things are small compared to this, what I am saying is that these things together will contribute to less than 1/2 of this in absolute value. That is what it is saying. That is what I am saying. Mod Pz is greater than or equal to 1/2 of mod z to the power n outside a large disk. Outside a large disk. Now from the previous one, we can now say that suppose Pz is not 0. Suppose Pz is not 0, then look at 1 over Pz. Outside this disk, what is 1 over Pz? Mod Pz is greater than or equal to half mod z to the power n. So 1 over Pz absolute value is less than or equal to 2 upon R naught to the power n. That is a bound outside, but inside the ball, inside the disk, closed disk, 1 over Pz is continuous. So it is bounded. So inside this disk of radius R naught, it has a bound. Outside the disk, it has a bound, namely 2 by R naught to the power n. So it is bounded. So by Liouville's theorem, Pz will be constant. So if I assume that a polynomial Pz is not 0, that means that 1 over Pz will become a bounded entire function. So by Liouville's theorem, it is a constant. So every non-constant polynomial must have a complex root. The fundamental theorem of algebra follows from the Liouville's theorem, correct? That is what the exercise is saying. Is it clear? Now a few concluding remarks. So now power series provide us with a large supply of complex differentiable functions. Suppose you take a power series a0 plus a1z plus a2z squared plus etc. Suppose that this power series converges in a disk of radius r, mod z less than r, then f is complex differentiable on this disk, because I can differentiate term by term, isn't it? So it is complex differentiable. What is the complex derivative? A1 plus 2a2z plus 3a3z squared, etc. But this power series also has radius of convergence r. So I can differentiate it again. So f prime is again complex differentiable. If f prime is again complex differentiable, that means that f prime is continuous in particular. What is our definition of analytic function? An analytic function is a function which is complex differentiable and such that u sub x, u sub y, v sub x and v sub y are continuous. In other words, f prime should be continuous. That is our definition of analytic functions, correct? So the sum of a power series is a analytic function within the disk of convergence. So the power series give us a large stock of complex differentiable functions. Indeed, they give us a large stock of analytic functions. Okay. So now in this concluding piece, we now do one more important theorem on power series, but this time we will look at a power series with finite radius of convergence. We have been looking at power series with infinite radius of convergence. Now let us take a power series with finite radius of convergence. Let us assume that the radius of convergence is 1, just for simplicity. You can write down a corresponding theorem for in the general case. The theorem is Abel's limit theorem. What is the Abel's limit theorem saying? Suppose that a0 plus a1z plus a2z squared plus etc. is a power series with unit radius of convergence and the sum function is f of z. Suppose further that if I take this sequence of coefficients and form the corresponding infinite series a0 plus a1 plus a2 etc. converges. So what are you given? You are given a power series with unit radius of convergence and some function fz, and you are also given that when I put z equal to 1 in the series, it converges. Then limit fz as z tends to 1 along the real axis. Limit fz as z tends to 1 along the real axis exists, and the limit and this limit equals a0 plus a1 plus a2 plus etc. Now why is this Abel's limit theorem an important theorem? I mean, it looks more like a technicality, right? Why is this theorem an important theorem? What is Abel's limit theorem again? a0 plus a1z plus a2z squared plus a3z cube etc. is a power series which converges in the unit disk and the sum is f of z, and a0 plus a1 plus a2 plus a3 etc. is a convergent series. Then limit of f of z as z tends to 1 exists. Remember, 1 is on the boundary. 1 is on the boundary of the disk of convergence. Limit of f of z as z tends to 1 exists and equals a0 plus a1 plus a2 plus a3 etc. Why is this so important? The reason is very simple. Suppose I take the limit of f of z as z tends to 1. Suppose I try to do this. What is f of z? F of z is summation. What is f of z? F of z is summation a n z to the power n from 0 to infinity. What is that? That is limit as n tends to infinity, k from 0 to n, a k z to the power k, correct? Now, if I am able to interchange these two limits and write limit as n tends to infinity first and then limit as z tends to 1, then that is a finite sum. And I can take the limit of z tends to 1 inside the finite sum and I can write it as limit as n tends to infinity summation a k. But limit as n tends to infinity summation a k is k going from 0 to n is again sigma n from 0 to n, n from 0 to infinity a n. So, but what the Arbels theorem is asserting is that this is equal to this. This step and this step is trivial, just a definition. This equality is trivial. What is non-trivial? The non-trivial part is this. So, Arbels limit theorem is essentially a theorem about exchanging two limit operations, and that is why it is a deep theorem. It is deep, but it can be done in a course like this. It will take me about 15 minutes to prove the theorem, or perhaps or something of that sort, but I do not have time to, I do not have those 15 minutes to prove Arbels limit theorem. So, we will not prove the theorem, it is there in many books. I mean, you can read any book on, it is then Rudin's Principles of Mathematical Analysis, if you want. No, Rudin's book, Principles of Mathematical Analysis by Walter Rudin, chapter 8, 3rd edition. You will see the Arbels limit theorem. He calls it the Arbels continuity theorem. No, not chapter 8, chapter 3, sorry, chapter 3, it is on numerical sequence and series. Some exercises for you now. Show that if z equal to x plus iy, then mod sine squared z is sine squared x plus sinh squared y. Mod cos squared z equal to cos squared x plus sinh squared y. Second question, show that if u is harmonic on C and v is its harmonic conjugate, then cos u cos v is harmonic on C. Show that if u is harmonic and v is its harmonic conjugate, then cos u cos v is harmonic. How will you do this? Directly by calculating the Laplacian? No. U is harmonic and v is its harmonic conjugate. So, u plus iv is analytic, right? U plus iv is analytic. If u plus iv is an analytic function, then cos fz is also, call u plus iv f. Cos is also analytic, so composite of analytic function is analytic. So, cos of u plus iv is also analytic, but what is the real part of cos of u plus iv? Cos u cos v, and being a real part of an analytic function, it is harmonic. Alright, clear? Determine the zeros of sin z and cos z. Determine the you can assume that the real zeros of sin, you can assume that sin x, you can assume the properties of sine and cosine on the real line, because we are not doing real analysis, that is supposed to be done in the real analysis course. The properties of sine and cosine on the real line are considered known. Use that to determine the zeros of sin z and cosine z in the complex domain. So, in particular, sin z will vanish at 0, plus minus pi, plus minus 2 pi, plus minus 3 pi. Question is, are there any other zeros? Are there any other zeros? That is the question. Find the largest domain on which e to the power z upon sin z minus cos z is analytic. Then the next is to find the sum of certain series, 1 plus cos theta plus 1 over 2 factorial cos 2 theta plus etc. Find the sum of the series. So, here you find the sum of the series. Sin theta plus 1 over 2 factorial sin 2 theta. So, these are from Hobson's book, E.W. Hobson. Plane trigonometry. Is an old classic. Hobson's plane trigonometry is a old classic. It's a beautiful book. I think you should order it for your library if your library does not have a copy. It is reprinted by Dover. It is reprinted by Dover Publishers. I am sure your library was, any old library will have it, because it has existed for a long time. There is one more problem of that kind, the part D. 1 over 4 factorial sine to the power 4 sine 4 theta plus 1 over 8 factorial sine 8 theta, etc. There's one more problem from Hobson's book. Show that the coefficient of z to the power n in the expansion of e to the power z cos z is root of 2 to the power n upon n factorial cos n pi by 4. This is also from Hobson's trigonometry. Then the next question, question number 6 is you take the roots of unity, the kth roots of unity. The last one, the kth one you call it 1, okay. Zeta sub k is 1. Then prove that 1 minus zeta 1, 1 minus zeta 2, etc. 1 minus zeta k minus 1 is k. 2 raised to n, yeah. Root of 2 raised to n upon n factorial cos n pi by 4, right. Prove that if zeta j from 1 to 3 up to k denote the kth roots of unity with zeta k equal to 1, then 1 minus zeta 1, 1 minus zeta 2, etc. 1 minus zeta k minus 1 is k. Deduce from this that the product j from 1 to k minus 1 sin j pi upon k equal to k by 2 to the power k minus 1. Those who were in the last course will remember this. This appears in some theorems concerning the gamma function. When you prove the Gauss product formula for the gamma function, when you prove the Gauss's generalization of the duplication formula for the gamma function, you use this property. Remember, we had done it in the last course as an application of Wieland's theorem. The normalizing factor had to be determined, and this was crucial. All right, shall we proceed to the next one? 7th question. Let fz equal to z minus z squared upon 2 plus z cube upon 3, etc. Prove that f prime z equal to 1 over 1 plus z, and so 1 minus half plus 1/3 minus 1/4, etc. is log 2. We have not discussed complex logs, but we don't need that here. All that you really need is a real case. You can restrict z to the real axis. You have to use the Arbels limit theorem, by the way. This is not a trivial problem. You need to use Arbels limit theorem. And the next one is very similar. 1 minus 1/4 plus 1/7, etc. is 1/3 log 2 plus pi by 3 root 3. Hint, start with sigma n from 0 to infinity minus 1 to the power n z to the power 3n plus 1 upon 3n plus 1 and differentiate. This problem is from Konrad Knopp's book Theory of Infinite Series. Knopp's small Dover book. You want the previous one? 7th one? 9th one. Prove that 1 minus 1/3 plus 1/5 minus 1/7, etc. is pi by 4. This is normally attributed to Gregory. However, recent findings show that this series was known to Madhava. So I should call it the Madhava series, I suppose. But it is traditionally attributed to Gregory, but apparently was known to Madhava also. So Madhava series. 10th problem is very interesting. Let fz equal to sigma n from 1 to infinity z to the power n upon n squared. Its radius of convergence is 1. Prove that z f prime z prime equal to 1 over 1 minus z. So I can restrict myself to the real domain. I can start with this equation. Restrict yourself to the real axis minus 1, interval minus 1 to 1. Put z equal to x and let x vary between minus 1 and 1 and integrate. Integrate and you get this result, and then you get f of x. F of x is an integral 0 to x ln of 1 minus t upon t dt. Then allow that x to go to 1 and use Abel's limit theorem, and you will get that sigma n from 1 to infinity 1 over n squared is minus integral 0 to 1 log of 1 minus x upon x dx. The right hand side is an improper integral, mind you. You have to first discuss its convergence. So, right hand side is an improper integral. This function fz is called the dilogarithm. And this integral is called the Spencer's integral. Dilogarithms and is a first of a series of hierarchy of functions called polylogarithms. The literature on polylogarithms is very vast. There is a book by Levin, you can consult the book, Levin, Polylogarithms and Associated Functions. Polylogarithms and associated functions. Okay. So, with this I conclude lecture number 4, and tomorrow we will start with the complex logarithms and inverse trigonometric functions and other things. Okay.